So we've just seen how we can use mathematics to represent signals that have some sort of physical meaning from the real world. Now, oftentimes we're interested in how much energy is that signal carrying. And for systems, we're interested in how much energy is the signal carrying before entering the system versus how much energy is that signal carrying after leaving the system. So in this video, in this lecture, we're going to see how we can begin to define energy and power, and then how we can begin to calculate energy and power as well. All right, we'll start with an example, and you should remember from physics that the energy in a spring mass system was this 1/2 kx squared thing. Okay, and here 1/2 is a constant. Of course, k is a constant as well. That's a spring constant. X is what changes. If you don't remember, x is the displacement, or the distance away from the equilibrium the mass is. So this is what's changing with respect to time. And notice that there's a square there. In circuits, you may have seen, and related to energy is power, in circuits you may have seen something like the power absorbed by a resistor is V squared over R, or I squared R. I'll even write that here, I squared R. And in circuits, it's the voltage that changes with respect to time if it's AC circuit, and R is just a constant. And similarly, the current changes with respect to time. That's our signal. R is just a constant. So in all three of these cases, and there are many, many, many more, the energy and the power are related to the square of the signal. This is almost always the case. And in our class, we want to be able to apply these methods to any situation, not just electrical engineering, not mechanical engineering, any sort of situation where we have a system and an input and an output. And so we're not really interested in units in our course. And so we're going to drop R, and we're going to drop the 1/2, and we are going to define energy. We're going to call this the total energy in the signal, E sub infinity. We're going to integrate then over all time, right? We're interested in the energy over all time, the absolute value squared of the signal. I call this the energy over all time. Okay, and sometimes I get the question, why absolute value? Isn't squaring making it positive anyway? Well, as you will see in a few more videos, our signals can be complex, meaning they have a real part and an imaginary part. And squaring a complex number is not what we want, depending on your level of comfort. And you might understand this, you might not, but what we want is the absolute value, or the magnitude of that complex number. So magnitude of the complex number squared. So the magnitude there, the absolute value, is a kind of a fail-safe for when we have a complex signal. And in discrete time, we are going to define the energy not by an integral, because an integral is a continuous idea or concept. Think about calculus and how the integral was defined. It makes no sense to integrate in discrete time. What we're going to do in discrete time is just sum from minus infinity to plus infinity of the square of the magnitude of the signal. And so this is how we will define energy in a signal over all time. Okay, and again, we're not really interested with units, so we're leaving off all these proportionality constants. Now, related to energy is power. And you should know that power is a rate. It's the rate of energy. And so if we look at just the continuous energy for now, it's kind of double-sided infinity, where you're going to positive infinity and you're also going to negative infinity. So speaking loosely, you could say that the time frame here is twice infinity. So if we calculated the average power or the energy over all time and divided it by twice infinity, then we would have the power over all time. This is kind of this is not good notation in mathematics, and so what we define average power over all time as a limit as some capital T goes to infinity of 1 over 2t times the integral from minus t to plus t of the square of the absolute value of the signal. Okay, so in this limit, notice as t goes to infinity, then our bounds of the integral go from minus infinity to plus infinity, and this integration then is exactly the energy. And so then we take that energy and we divide by twice infinity. And so that gives us, like we thought, the average power. Average power over all time. Okay, and not to be outdone, in discrete time, we're going to say the limit as some capital N goes to infinity of 1 over twice that capital N plus 1, a summation from negative n to positive n of, again, the square of the absolute value of our signal. And this is how we define average power. Now for the discrete time case, notice again, as n goes to infinity, we have kind of this double-sided infinity. So that is the energy, right? That's the energy. Then we divide it by this twice infinity to get the power. And you might be interested in, well, why is there a 1 there? And the idea is that we want to divide by the number of samples, the length of time. And in discrete time, if this is the origin and we have some signal, right? Maybe this kind of signal here, here's n, and we have a signal here. Maybe this is minus n. And you say, well, how many points is that related to n? Well, we have 1, 2, blah, 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 up to n this way. And we have 1, 2, up to n this way. So we have 2n. Then we have the 1 at the origin. We have the 1 at the origin. So we have a total of 2n plus 1 points. So here n is shown as 3. 1, 2, 3. Then negative 1, negative 2, negative 3. So how many points do we have? We have 2 times 3 plus 1, or 7 points there. So that's where the 1 is coming from. It's kind of just a formality there. Okay, so now from our definitions, there are 3 different types or classes of signals. Classes of signals based on these definitions. First of all, when we compute the energy, we could get a finite number. Call that finite number E. Okay, so it might have a finite amount of energy. So let's just work on the continuous case for now. So if you lock in on this integral, this would be a finite number. And then notice the power, what this implies about the power then. So this integral is finite. Then you divide by something that goes to infinity. So when you take a finite number, the energy, divide by something that goes to infinity, then you have 0. So when the energy is finite, this implies that the average power is 0. Okay, that's one type of signal. A second type of signal, and let me give you an example of that first type. So let's say we had something like this. It's 0, the signal is 0, but like a little triangular pulse. Maybe that's our signal. When you calculate its energy, you square the pulse, and so this is still 0, and this is still 0 after squaring. And then you add up all of the area, right? So that's a finite number. And so the energy is finite, but then when you divide by all time, you get 0 power. Another type of signal is when the energy is infinite and the power is finite. We'll call that P. Okay, let me give you an example there. A DC signal. A DC signal is a signal that doesn't change. Now, let's think about the energy in this guy. If I squared it, okay, then its amplitude would still be non-zero, and it still would not change if I squared it. And then if I added up all the area from minus infinity to plus infinity, that would go to infinity. And so the energy in that DC signal is infinity. But the power is a rate, right? It's the energy per time, the rate at which I am adding up that energy. And so for this guy, this signal, you'd see that that rate is constant, right? And so that rate does not go towards infinity, and you define that you'd get a finite number here. So this would be the second type of signal. And the third one then is when the energy is infinite and the power is also infinite. And let me give you another example there. Let's say you had a signal like this, something that kind of just keeps increasing. When you square it, then certainly the square keeps increasing, and then so when you add up the area, it goes towards infinity. So the energy is infinite. But the power is a rate at which that area is increasing. And so the rate is certainly increasing. So the rate of that accumulation of area goes towards infinity as well. Okay, so again, we've seen here now that we can define energy, we can define power, and we've come up with these equations so we can begin to calculate energy and power. All signals, discrete and continuous, fall into one of these three classes. So in the next video, let's look at some concrete examples about how we can start to calculate these things.